All right, so we're back. So let me recap. Um, just one second. Just want to make sure you guys can hear me okay, right?
Yep.
Okay, good. So let me recap what we've been discussing so far. So I'm using the idea of the fact that we have a conservative force. The electric field is conservative. Okay. Because the force is conservative, the electric field will be conservative because the electric field is force over charge. And as a result, I can define a potential energy. And we know from previous course that the work done by a conservative force is minus the change in potential energy. That's how we define it. And so that's what I've done here. And that allows me to define the change in potential energy. The actual potential energy we'll talk about too, but remember, potential energies are always known to within a constant. And so one of the things we have to discuss is how do we define our reference point? Okay, something like you did with gravity. Then we took this expression and then we divided it by Q naught, the test charge, because here we looked at the change in potential energy of the test charge as we move it from point A to point B in electric field. We divide by the test charge, and we get an expression for the change in the electrical potential. It's basically the electrical potential energy, or the change in electrical potential energy per unit charge when you move an object from point A to point B. Okay. And then the unit for this is the volt. And so because this is a difference, so we can write the actual value for U over Q as V. Okay, and we call this the volt. And I think you can see now if this is a volt, this is a distance, this can also be written as a volt per meter. Okay, so this can be written as a volt per meter. The same thing as a Newton per coulomb. So the electric field can be written in terms of volts per meter. And what's going to happen now is, pretty much from now on, I'm probably going to say volts per meter for the electric field. But realize that these are the same. And if you want to, you can try practicing to see that, because a volt is a joule per coulomb. So if you put a joule per coulomb here, then you can see you get a Newton per coulomb. All right, so what does all this mean so far? Well, the potential difference, you can think of it as the amount of work per unit charge that's required to move a test charge between 2 points in the presence of a field. So suppose you have a particle in the field. So let's say you have a particle Q here at point A, and you want to bring it to point B. And you have some field that permeates this whole board. My goal is to move it from A to B. So the work done by the field is just going to be the integral of Q B dot ds as you go from A to B. If you bring it from A to B such that the change in kinetic energy is 0, it means I have to apply a force to bring it from here to here so that the change in kinetic energy is 0. So I start with no kinetic energy and end with no kinetic energy. So then what is the applied work done? And arrow too low. Hold on a second. Let me move. Let me change my view here. Hold on a second. So W applied is going to be on the negative of this. But this is the change in potential energy. And so we say, so this is the potential energy. So the work that the applied force has to do is equal to the change in potential energy. I'll give you an example. Okay, another example. With gravity. If I take an object and I lift it from here, from my hand, to some distance above my hand, the work done by gravity is zero. I'm sorry. The work done by gravity is minus mgh. The work that I do in lifting the object from my hand to some location above my hand is positive mgh. The work that I did increased the energy. So the work that I did gave the system potential energy. The work that I did changed the potential energy by mgh. Does that make sense in terms of gravity? When I lift this up, I did work called mgh. Gravity did work minus mgh. The work that I did stored energy. The work the applied force does on a particle electric field stores energy, changes potential energy. And if I take that and divide by Q, then I can say that this is the work per unit charge that's required to move any charge from point A to point B. So that's a way to interpret this. Now, what can we learn if our field is constant? I have my integral. What can I learn if my field is constant? So what I'm about to say right now only assumes the field is constant. So let's take a look at this. Let me erase my board. My goal here is trying to figure out what this V means. I introduced this V. What does it mean? V meaning electrical potential. So assume the case where E is uniform. I should say yes. Then, when I look at my equation for the work done by the field, it's going to be the test charge on the integral of D dot ds. I can pull this out of the integral. Let's assume the angle between E and ds stays constant, and so I can write Q naught E cosine theta. I'm assuming E is uniform. But what if theta is 0? You move it in the same direction as the electric field. Then the work done by the field is going to be Q naught E. And then, so this is going to be your displacement. So let me write my displacement just as a letter D. And this is minus the change in potential energy. Well, let's look at this equation. If delta V is delta U over Q naught, then delta U is Q naught delta V. So I have Q naught ED equals minus Q naught delta V. And I'm just doing it, I can do this in general terms, but I'm doing the easy case. Let's cancel out the Q naughts. And I get E times D is minus delta V. And E is minus delta V over D. What does this mean? Other than the fact that the electric field is easy to calculate for the case where it's constant. Delta V is easy to calculate when it's constant. What does this mean? Notice that E and delta V have a minus sign represented in the equation. This tells you that the electric field is directed towards decreasing potential. The electric field points in the direction in which V decreases. That's always true. E is always directed towards decreasing V. It's very important for you to understand. Okay? And it comes from the fact that we define the work done by the field as minus delta U. Okay? But what it means, though, then, is that the electric field is directed towards decreasing V. So, if I have an electric field that points to the right, the value for V, which is a scalar, decreases to the right. So that means, V could be 100 volts here, and it could be 3 volts here. And the electric field points in that direction. Does that make sense? Okay. Sorry, just 1 minute. And so that's really what I wanted to do with this exercise. I'll show it to you in a more general case in a little bit. Suppose you have a proton that moves in the direction of the electric field. Okay, let's draw a picture. I'm going to use green because it's hard to see and I can write over it as my electric field. So the green that's hard to see is the electric field. I did that on purpose. Here's my proton. It's positively charged, of course. And it moves in the direction of the electric field. First question. If it's moving in the direction of the electric field, is it going to speed up or slow down?
It's going to speed up.
It's going to speed up. It's going to go faster, right? So delta K is bigger than 0. Okay. So delta K is bigger than 0. What can you say about delta U? You might say, how do I answer that? Well, the force is conservative, energy is conserved. When you have conservation of energy, what equation do we write down for conservation of energy? Well, we know from the previous course that delta U plus delta K, what's that equal to? 0. So that means that delta U is minus delta K. So this is going to be less than 0. Does it make sense in terms of what we've learned before? Okay, let's try this. Does gravity point downward? I take this object and I drop it. What happens to its kinetic energy when I drop it?
It increases.
It increases. What happens to potential energy?
Decreases.
It decreases. Okay, so it's in agreement with this, right? So, but delta U is Q delta V. And Q is positive. So what does delta V mean? What happened to delta V? Does it increase or decrease?
Decrease.
It decreases. Hey, look, and this agrees. The proton is moving in the direction of decreasing V.
Also, that delta V acts kind of like your force, in a way.
I'm sorry?
In terms of that equation, delta V is like, it's not force, but it's kind of like the force because...
Well, it tells you there's an electric field. If you have a delta V, you have an electric field.
Yeah, and then from that field, there's an electric force.
Yeah, then you have
Okay.
because the force is Q times Z, you get a force. Yeah. As long as you have a charged particle in the field. Now let's repeat this for an electron. Suppose I have an electron. By the way, don't try to. When I was a student, I always tried to just memorize these, and it would screw me up. Okay. Every time I ask this question, I actually have to go through. For me, I have to just go through this because it just makes logical sense. If you just memorize stuff, you're going to make mistakes. You're going to get all mixed up with the signs. Okay. So go through this thought process. So let's pretend I have an electron. It already has some velocity to the right. The electric field is to the right. Now you tell me what's going to happen to the kinetic energy.
Decrease, right?
I'm sorry?
It should decrease.
It decreases. It's going to slow down, right? Because the electric field wants to go against the direction of the electron wants to go against the direction of the electric field. So this is going to be less than 0. Okay. Notice that the electron is moving in the direction of the electric field right for now, until it comes to a stop. But, okay, so then what does that say about delta U then? If this is less than 0, what must this be? In order for this to be equal to 0, if delta K is less than 0, shouldn't this be bigger than 0? Now, here's the thing. If delta U is positive, Q is negative, what about delta V? Positive, negative. Should that be negative? The answer is yes. So delta V, again, is less than 0 because the particle is moving in the direction of the electric field, which is the direction of decreasing voltage. Right? And you can look at it in terms of a ball that's being dropped in the field, except that there's no such thing as a ball of negative mass, so I can't do that analogy. Okay. So, if a proton is moving so that it speeds up, it's moving in the direction of decreasing V. If an electron is moving so that it speeds up, is moving in the direction of decreasing V. It's moving against the electric field. But in either case, if they're both speeding up, delta U has to be negative. So when you're ever asked a question, you should go through this line of thought. Don't just try to memorize things. I mean, I would always mess myself up. I always have to do this argument. Okay. Some people are really good at it, but I think if you have trouble with it, just go through this argument, because this argument is not that complicated. You just got to know this equation and this relationship. Okay. All right. Simple problem. Let's find the speed of a proton that's accelerated from rest through a potential difference of 120 volts. And we can do this for an electron. Okay. It's a conservation of energy problem. So we're really doing an energy problem. So right now we're dealing with scalars, not vectors. But sometimes it's not. So I'm going to use the equation delta U plus delta K equals 0. All right. Let's say it says from rest, so let me make the problem a bit easier. Delta U is minus the change in kinetic energy, which is minus 1/2 mv final squared minus 1/2 mv initial squared. But this is 0. So delta U is minus 1/2 mv initial squared. Now, the delta U has to be negative if it speeds up, right? If we're dealing with a proton, that's the charge of the proton. Usually I don't put the numbers in it right away, but I kind of want to illustrate something. What must delta V be, positive or negative, for it to accelerate?
Positive?
Well, but if this is positive and this is positive, and there's a minus sign here, then I'm going to take the square root of a negative number to find V, right? Can I do that?
Oh, so it does have to be negative.
It has to be negative. Remember the
if your charge is positive.
Yeah, so this has to be minus 120 volts. Because remember the example I did, I had the electron moving in the direction of the field and it sped up. And it was moving in the direction of decreasing V. So that has to be negative. So now this negative sign and this negative sign cancel. So I have 1/2 mv squared equals 1.6 times 10 to the minus 19 coulombs times 120 volts. So that's my energy. Okay. And I can express, this is what's cool. Okay, watch this. This is my kinetic energy. This is in joules. What happens if I convert this to electron volts? What do I get for an answer? I got to divide by this number. So my kinetic energy is 120 electron volts. That's why we use that conversion. It cancels this number out. Does everybody see that? In the electron volts, it's 120. But based on canceling this number out. Now, however, if I got to find the speed, then I can't do that conversion. So V is going to square root of 2 times 1.6 times 10 to the minus 19. And what was the mass? We did a proton, so 1.67 times 10 to the minus 27. So if you do the math, you get 1.5. It's going to sound fast. Hold on a second. So it's going to 150,000 meters per second. Okay? It's going to 150,000 meters per second. That's how fast it's going. That's not even close to being relativistic. What if I do the electron? What changes here if I do the electron? Well, conceptually, this still stays the same, but the electron charge is negative, which means that this has to be positive. Of course, I still have a negative here, and I still have a negative here, so this is still the same. The energy is still 120 electron volts. Both the electron and the proton will have 120 electron volts. Okay? If you want it in joule, you're going to take 120 times this number. So now, instead of dividing by the mass of the proton, I'll divide by the mass of the electron. And I didn't have this number calculated, so let me calculate it real quick. It's going to be a lot faster. So it's going to be 6.4 times 10 to the 6 meters per second for the electron. So this is a proton. This is the electron. Okay. They both gain the same energy just because their masses are different. One's a lot faster than the other. What you might want to do is go over this video several times so that you understand it, because the logic can be sometimes it's really simple, but it can be confusing at first. Once you get it done, then you're okay. As a student, I used to always have trouble with this. Okay. It's really not a hard idea. Just you're keeping track of a lot of things, and sometimes that makes it hard. And you're dealing with positive and negative signs. All right, so I'm going to look at how do we calculate delta V for a point charge. Let's say I move a point charge between two places in space. Okay. And now I want to know delta V. Suppose I have a source of an electric field, and the source is just a point charge. This is the source of so this is a field source. And remember that the electric field, due to this thing, is going to be K cubed over R squared, R hat, where R hat is a unit vector that is directed. So from the source of the field to the point at which you're determining the field. We know that delta V is minus the integral of E dot S. So I want to know the electric field, how the potential varies by this point charge. I know that the potential is going to decrease as you go away from the charge because the electric field is directed away from the charge. So I have to integrate minus the integral of E dot ds. going to be minus the integral of this thing. So suppose I go from this point A to this point B. What's delta V? Whatever that path is. How does this thing vary? How do I go from here to here? Well, here's the thing. I forgot something. Here's the thing. When I calculate this integral, when I look at this dot product, I can break up this unit vector into two components. I'm sorry. I can break up this ds into two components based on how I define my coordinate system. I can break it up so that it has one component along r hat and one component perpendicular to r hat. And so only the component parallel to I hat will contribute. Which means that I can write this. And only the component of ds in the direction of our hat will contribute to my integral. Yeah, I know I'm being very general when I'm saying that. Some people don't like that. But I'm trying to be very general what I'm going to come up with. So this integral is easy. Actually, I should put r sub a and r sub b. That my pitch is bad. So delta v, let me rewrite it, is minus the integral of r sub a to r sub b of k q over r squared dr. And you all know how to do this integral. K q, because the integral of this is just 1 over r, right? And the minus sign does come out. And so this is going to be v sub b minus v sub a. That's delta v. So that's it. You can tell that the electrical potential depends on 1 over r if your source is a point charge. And if B is bigger, you can see if B is bigger than A, that this function gets smaller, which makes sense because the electric field is pointed away from the charge, and we said that the electric field is directed towards decreasing V. Now, the actual value of V is arbitrary. Same like gravitational potential energy that you learned in the previous course. So what I'm going to do is, I'm going to let R sub A be infinity. So let R sub A and let V at R equal infinity to be 0. You did this for gravitational potential energies. So what does that mean? Well, it means that this is 0 and this is 0. So then I can say V sub B equals V equals K Q over R. I can do it in general. So this is the value of V at any location in space due to the point charge, assuming that we define V to be 0 at infinity. This is an important point that's really hidden in introductory level in course. That R represents a unit vector. That R represents the magnitude of a vector that is directed from the source of the potential to the point at which it measures. That's important. Okay. You really don't see that effect here, but you would see the effect in the junior level class. You actually need to know that. Okay, because there are some charge distributions for which you could derive the electric field from the electrical potential, and you'll make some weird mistake with the minus sign because you don't realize that. So that R is the magnitude of the vector that points from the source of the potential to the point at which it's measured. I used to do an example illustrating the issue with this, but I didn't have time. Maybe if I have time, I'll make a video. Okay. So suppose I calculate the electric potential just through a bunch of point charges. Instead of having one charge, what if I allow it? I just got to add it. This works by superposition. To scale it, I just use the principle of superposition. So if I have two charges, I just add things. It's very easy to find the electrical potential due to a system of point charge. By the way, I got this equation from this. This works in every single case. This expression works in every single case. This does not. This only works if I have a point charge or I have a charge distribution that is finite in size, in which I can break it up into small dqs. So that's an important point. Because if I have an infinite plane, and I want to find the delta V due to an infinite plane, I can't use this. But I certainly can use this. Because an infinite plane is infinite charge. Okay, so it's simple to find the potential due to a system of point charges. Suppose we have 2 point charges. What is the work required to bring the second charge in the vicinity of the first one? Actually, how much work does it take that orange charge you see in the slide there? Let's assume it's isolated. How much work does it take to put that charge there on the screen? Well, if there's nothing around, no work is required. We're assuming no gravitational forces. Okay. I know that sounds weird. If all of a sudden I take some charge from infinity, from really far away, and I've isolated, it's completely isolated, right? I put the charge right here. I'll call it Q1. No work is required to put that there because there's no field. I'm not doing work against any field, so no work is required to put it there. Because remember, the work that you have to do, plus the work done by the field, has to be 0. The delta K is 0. So, if this is 0, that's 0. That's how much work I have to do. But now, what if I have to take a second charge and bring it here? How much work does it take to put that guy there? Well, now I'm going to work against this field. So the potential due to this guy, remember, we just derived it, V due to Q1 is K Q1 over R. So the work I have to do is just delta U. So when this object is at infinity, initially, then this is 0. When it is at location R12, then this V final is K Q1 over R12. And so the total energy is K Q1 Q2 over R12. That's how much work I have to do to put this guy here. In fact, that's how much work I have to do to assemble the system of particles. If I bring them in from infinity.
It's the same.
It's the same as...
Why is what you use for KQ1, Q2, right? Because the first one takes 0 work and the second one takes that much work.
Yeah, so this is the potential energy of the system. So this is the delta, this is the U of the system, the U for 2 charges. Okay? I'm assuming U initial 0. I'm assuming V initial 0. Because the work that I have to do stores energy in the system. If both charges are positive, I have to do positive work to assemble this thing. I have to push them toward each other because they want to stay apart. They want to break apart. If one of them is negative, I have to do negative work to put this together. That's important. If I have to do negative work, that implies I might have a system that can form a molecule. And you might say, well, you can't have a stable equilibrium. Well, it's not a system that's in equilibrium. But I can form a stable molecule if delta U is less than 0. If the work that I have to do is less than 0. Because it means that the system wants to stick together. When you look at all atoms, you look at the electric potential energy of the electron in an atom, they're all negative for the case where they're stable. Once it becomes positive, the electron it gets kicked out of the atom. So let's say I want to figure out how much energy is required to assemble those 3 charges. How much energy do I have to do? How much work do I have to do? Well, I've done part of it already. To bring 2 of them together, is the amount of work. Okay. Now, I bring a third one. So let's say, for the first 2, and the geometry doesn't matter really. If I take the third one and put it right here, I have to do work against the field due to this guy, Q1, and I have to do work against this one too. And then I got to calculate that work and add it to this. And that gives me the amount of energy required to assemble the entire system. So to bring Q3 here, I'll just say W3. That's going to be equal to Q3 delta V due to charge 1 plus Q3 times delta V due to charge 2. So if I call this distance R13, or R3 when it doesn't matter, and I call this distance R23, or R32, it doesn't matter, then I can work this through. Because then I can say this is equal to Q3 times K Q1 over R13 minus K Q1 over infinity, 0, plus Q3 times K Q2 over R23 minus K Q2 over infinity. Well, this guy ends up being together K Q1 Q3. I'm not sure you can see that. Sorry. You can see that good. K Q1 Q3 over R13 plus K Q2 Q3 over R23. So that's how much work it requires to put the third charge there. This is how much work it requires to put the first two there. So the total is going to be this plus that plus that. Does that make sense?
Yeah.
Okay. Now what if you did 4? I don't want to do 4. 4 would have 3 more terms. Okay. But you could write it as a general expression. And you can actually have a computer do it for you if you have like 10 of them.
And so why would 4 have 3 more terms? Oh, because it's another. Okay.
Yeah, because then the fourth one would have to do work against 3,
3,
2, and 1.
In terms of calculating total work on the system, right?
I'm sorry?
When calculating total work on the system, but just on one point against 3 other points is just 3 terms, right?
Yeah.
Okay.
If you have 3 charges.
Yeah.
Yeah. Okay. So you can write this in the general form. Let's say if you wanted to do this on a computer. You can write it this way. You can write it as a summation. Why is there 1/2 there? I'm summing over all i's and all j's. Why is there 1/2 there? Because the way I've written that summation, included in the summation is the case where these numbers are flipped around. Okay? Included in that is the case where these indices are flipped. And so you're double counting. Those are the same value. So if you write it as a summation like that, you're double counting, so I have to multiply by 1/2. And I got to make sure I is not equal to j. Okay. Now, how do we obtain now the electric field from V? How do we obtain the electric field from our knowledge of V? And I start with the idea that, from this definition. I know that delta V the electrical potential difference is minus the integral of E dot ds. If I don't integrate, then this is really a dV. Okay? Which means, if I'm in a coordinate system, in a rectangular coordinate system, I don't want to do this in general. If I'm in a rectangular coordinate system, then dV is going to be E sub x, minus E sub x dx plus E sub y dy plus E sub z dz. The x component times the x, the y component times dy, the z component times dz. And that's it. Okay, so what?
And what's ds again? Sorry.
Oh, it's the path. It's an element of the entire path, an infinitesimal element.
So it's like dr basically, but not at starting at the origin.
Well, it could be anything really. It could be a dr or whatever. Sometimes in books they use dr. Sometimes we use ds. So for
Okay.
every time I've in 205 in this class, when I integrate over a path, I write ds.
Okay.
And if you've had Calc 3, this is called a path integral.
Yeah.
Okay. And I'm not going to really talk about it in terms of that. I mean, in Calc 3, you do all kind of interesting path integrals. All right. And you learn how to do things in general in Calc 3. So, E sub x, if you think about it, suppose ds is just in the y direction. I'm sorry. Suppose dx is just in the x direction. Suppose ds along x only. Then dv is minus E sub x dx, which means that dv over dx equals minus E sub x. I can do the same argument, say suppose it's along the y direction, right? And then these will be y's. If I do the same argument for the z direction, then these will be z's. So basically what I'm doing is I'm taking the derivative of v with respect to x, assuming y and z are constant. Let's call a partial derivative. So you can write it like this. That's what I did here. I assumed that I look at how v varies along x only, and I kept the other ones constant. And so these got so the electric field components are based on a derivative. So minus dV dx is E sub x. Minus dV dy is E sub y. Minus dV over dz is E sub z. So we can say then that the electric field vector is equal to, if I read it in terms of all its components, dV over dx I hat plus dv over dy j hat, and I gotta multiply this through by -1. And there's a fancy symbol that's used for this. It's called a gradient. And look, I'm not being rigorous in discussing this mathematically. Okay, I can do that. I just don't have time in this class to do that. At least it might get totally beyond the scope of the class. So I'm going to be not very rigorous. The math folks probably wouldn't like the way I'm doing it, but I'm just doing it for it. Just to show you that it's related to something. This is called a gradient. We're not going to do a lot with this because it's a calc 3. If you had calc 3, you've seen that upside down triangle, right? The bell symbol.
Professor, is that like 2 J's, J hat?
Oh, yes, sir. Thank you. That's okay. Thank you very much. Okay, now it's better. Okay now? We okay with this? So, the electric field is called a potential gradient. I mean, mathematically, the electric field represents how the electric potential varies in space. By the way, I can write this, I found one, but I can write this as a dot product between the electric field vector and which I had before. Okay. But I can write it as a dot product between the gradient and ds. Okay. But I don't want to get into that. Maybe I said too much. Okay. So suppose I'm given an electric potential like the one shown in this slide. I want to find the electric field. Well, it's easy. Okay. All I got to do is take the derivative of that potential with respect to x, then I will take the derivative with respect to y, and then I take the derivative with respect to z. And each derivative will give me each of the components of the electric field. I'm going to do E is equal to minus the derivative of that equation that you see in the slide with respect to x. If I take the derivative just with respect to x, then I just get 3,000, and then I take the negative of it. And I know you see partial derivatives before because you've done air propagation. I will do it too. If I take the derivative of that function with respect to y, what do I get? Oh, there's no y in that thing. And I know I probably shouldn't write that. I take the derivative of that function you see, and maybe I should write it out, I apologize. V per volts. If I take the derivative of this function with respect to z, what do I get? Don't I get 3,000 z? And then I got to take the negative of it because of the negative sign. It shouldn't make sense volt per meter because I'm taking volts divided by meter. Are we okay on that?
Yeah.
There's a lot more to this, but we're not going to do a lot with this. Just so you're aware of the relationship between the two. But I'm going to do one more thing with respect to this. Let's look at this. Let's look at the case where dV is 0. You move along the path where this thing is always 0. This either means E is 0, or E is perpendicular to ds. Right? The dot product is 0, that means it's sort of perpendicular to each other. I don't care about this case. Okay, that's obvious. Hold on to this case. Either way means V is constant. So you're taking a path where V is constant. All surfaces that if these paths fall on the surface, these are called equipotentials in 3D. In 2D, it would be equipotential line. In 3D, it would be called equipotential surface. What this means is that the work required to make it move around there is to make it move around this path is 0. No work is required to make particles go around this path. Because E is perpendicular to ds. So any surface consisting of a continuous distribution of points at the same potential is called an equipotential surface. And it has some interesting application. It's a useful idea. The electric field lines are actually perpendicular to equipotential surfaces because E is perpendicular to ds. And you might be saying, well, so what? Well, let me draw a picture. Let me draw a picture of a point charge. Because that's the easiest one to see. And what I'm going to say is true in general. Here's a point charge. Okay. And we know that V for that point charge is K Q over R. That means for any value of R, V is the same. Right? For any value of R is the same. So I can draw a circle of radius R, and V is the same all the way around that circle. In 3D, it would be a sphere. I can draw another one. The value of V will be different because the radius is different, but this is also an equipotential surface. I'll call this R2. I'll call this R1. So if I move a particle anywhere along this path, really no work is required because the V doesn't change. I'm moving perpendicular to electric field. So no work is required. But since E is perpendicular to the S, this is a surface which is perpendicular to the S, then for me to draw an electric field, all I got to do is draw lines perpendicular to the surface. Right, perpendicular, perpendicular. Perpendicular, perpendicular. So I can actually map out the electric field from my knowledge of these surfaces. Before we had computer software to do our calculations for us, people who work on accelerators, if they wanted to design a system to change the direction of the particle inside the accelerator, they probably didn't have the ability to do the calculation because they're hard calculations. What they would do is take the conductors. There's this thing called conducting paper, and they would paint the conductors onto the paper. They would get a meter called a voltmeter, and they would measure the locations where V was a particular value. So they would use a meter and they would measure locations, let's say where the potential is 1 volt, 2 volts, 3 volts, etc. And then they would draw lines perpendicular to those and say, this is the electric field. That's it, they'd be done. We're not using a supercomputer to do the calculation. It gives you insight into a system. That's why this idea is important. Give you some insight. So, if you have a conductor, the surface of a conductor is an equipotential. Why? Why is the entire surface of a conductor an equipotential? Because the electric field inside the conductor is 0. E is 0 inside a conductor. So the electric field at the surface is an equipotential. In fact, the electric field points perpendicular to the surface. Right? The field inside a conductor is 0, and outside the field points perpendicular to the surface. And so the equipotential surface of the surface of a conductor forms the equipotential. Because 1 inside is 0, but really 2, the main one, really the important one, is E has to be perpendicular to the surface. Suppose I have a uniformly charged conducting plate. Okay? And let's put a charge right here. Actually, let me just do a conducting plate. What are the equipotential surfaces? Well, since the field lines of the plate look like this, then the equipotential surfaces are going to be planes that are perpendicular to these field lines. And so the green lines that you see are various surfaces of constant V. Suppose now I have 2 grounded conducting plates. And so these are grounded. And I put a charge here, Q, make it positive. What's going to happen? Well, I'm going to draw the field lines and the equipotentials, because in this particular case, it's actually easier to draw the equipotentials from the electric field. If this is positive, and these are grounded, what's going to happen is this positive charge is going to draw negative charge on this surface. And so the electric field lines are going to start perpendicular here. Drawing perpendicular to the surface. It'll look like that. Right? It's not an easy problem to solve. I mean, actually, it's not that bad, but you have to learn a special technique and you can solve it. So these are the field lines, and here's the equipotentials. Here, it takes on the shape of the surface. So I draw blue lines that are perpendicular to the electric field. As I get closer to the charge, the lines get more rounded. The blue lines are the equipotential surfaces. The red lines are the field lines. And the black thing is the electric, the plate. Okay. And the plate's grounded. All right. So now what I'm going to do is focus on calculating the electric potential. I'll do the case for a discrete charge distribution, and then do the case for the continuous charge distribution. I might only have time for the discrete one. Okay. Okay, so using the concepts we discussed, I want to write an expression for the electrical potential at point P. And I want to derive, I want to talk about the electric field at point P. Let me draw a picture. Now we know a lot about the electrical potential. I just want to spend some time calculating it. And then I'm going to be, when I've done these examples, the only thing I want to do is talk about a couple of applications. How many applications I do just depends on how much time I have. All right, so I have a charge plus Q here, and a charge minus Q here. And so I'm going to draw a coordinate system. That's supposed to be a straight line. Here's point P. And I want to calculate the field, electric potential at that point. Okay, this is Y. And this distance is A. So it's actually not that hard. I just got to use this equation. Take Q over R. So the V over here, I use the principle of superposition. And so all I do is say, the distance from here to here is Y. That's the first term. Second term, this distance is going to be Y squared plus A squared. I'm done. That's my electrical potential at point P. If I put a positive charge there, or a negative charge, I multiply this by whatever that charge is there, and then I have the potential energy of that object. What if I want to find the electric field? What's E?
Isn't E the sum of QV?
Well, I can find E this way, right? I can find the sum of K, Q sub I over I sub I, R sub I squared R hat, right? I can do it this way. Right? Because you said QV, that's the force.
Maybe QV, right?
No, that's the potential. That's
Okay.
I just want E. So this is one way. I don't want to do it this way, but this is one way to do it. We know, right? We've seen that we can take derivatives of this guy to figure that out. We know that E is, all right. This is a two-dimensional problem, okay? So we're in a two-dimensional world. But the third comes in 0. So I got to take a derivative with respect to x and a derivative with respect to y. So I don't have any x's here. Really, what I want to do is look at how this function varies. So I have to rewrite this first of all. I need to rewrite it so I can figure out how it varies. I'm going to write it like this. Right, because this is this function evaluated at a. So I want to see how this function varies with y and how it varies with x. So let's say I take a derivative of this with respect to x. What does that give me? I mean x. If I take a derivative with respect to x, and I got to multiply by -1, please help make sure I didn't make any errors. Does that look okay?
I think so. Yeah.
No, I'm okay. All right.
Well, besides the negative, right?
Yeah, but when I take a derivative, this is.
Oh, it's negative x, right?
Yeah, that cancels.
Yeah. Okay. Yeah.
Okay. So that's the first one. Then I got to take the derivative with respect to y. All right. So when I take the derivative of this term with respect to y, another minus sign will come out, and I'm going to get this. And when I take the derivative of this with respect to y, minus signs will cancel. Again, check my math, okay? But I got to do one more thing. Derivative with respect to distance. Yeah, right, because we're seeing how this varies everywhere in space. So it's, I don't want to say distance, but I want to take the derivative with respect to position. Right. We're differentiating with respect to position, not distance. Okay. So are we okay with that? If I said distance, I apologize. I mean by with respect to position. I got to do one more thing. What is the next thing I got to do?
Would you plug back in your points or not?
Yeah, I got to plug it. I got to put my a back in. So I don't want to rewrite the whole darn thing. I'm going to cheat. And right here. Now I'm done. How do you check that? Go ahead and do it this way. You better get the same answer. I get worried. It seems like no, we're fine. You do have to put the actual value of Q in there. Yeah, I made a mistake.
And you can factor out KQ though, right?
I'm sorry?
No, you can factor out KQ. Or is
Yeah,
that-
you can
oh,
factor
okay.
that out. I'm worried about the sign due to this term.
Oh, it would be
Because the field component's got to point downward.
the KQY squared term is negative in your final list. It should be negative, right? Because the negative is distributed to both terms, and both of those derivatives make a negative
You're
1.
right. So this has got to be negative. I screwed up. Thank you. Okay. That bottom, it's got to, right? Because I checked. Does it make sense with the physical picture? Okay. And if it doesn't, I did something wrong. So that's how I check my answers, right? I look at it. It doesn't fit with the physical picture. That tells me I did something wrong. Okay. Yeah, you're right. Because I have a negative here. I take a derivative, I get a negative, and then I have another negative there. So I have 3 negatives. So there should have been a negative there. So I did it too fast. My bad. So I don't want to start this now because this is a long-winded thing, and I am not going to make a video of this and skip this because it's too important. So next week, and I will extend the homework. Okay, don't worry about that because I have a bad date for this homework. For homework 3. So the next step now is calculating the electric potential due to a charge distribution, which is a little bit easier than for the electric field. All right, it's a little bit easier than for the electric field. So we'll do this next week, okay?
Is the test next week?
I'm sorry?
Isn't the test next week?
No, it's on the 25th.
Oh, it's the week after. Okay.
Yeah. And I actually was worried. For some reason, I thought it was next week, but it's not. It's on the 25th. So that makes me a little more comfortable. The lab next week, I'm going to start something new. You're going to start learning how to use a tool to measure current. So that's going to be probably one of the most important labs you do this semester. Because you're gonna build circuits, and if you don't make the measurements right, you're going to be blowing fuses constantly. So this is a lab where you're going to have to learn how to do things correctly, or you're going to have a lot of trouble with the labs. And Tyler will start. I will talk to Tyler. He'll start making videos to help you guys out. All right, I got to actually run to a meeting. So you all have a good weekend. I'll see you on Monday, and hopefully I answered your question. Okay. All right. Have a good weekend.
All right. See ya.